this is what we also want to do practical. But the idea is now that we have many namespaces or virtual machines. Doesn't matter. It could also be virtual machines. You have a virtual bridge here. Typically, the virtual bridge is attached to a physical interface because it makes the internet connectivity of the host machine. Yeah? And you have these virtual links here, which you also know already from the previous task of network emulation, to make the connection to the bridge. But this is not a complete picture because you would also need a VLAN IDs and stuff like this. But this is the idea. You have a bridge, and the bridge makes the connection for the network devices, yeah, to the internet, to the outside world, to the TSN network here. Yeah? Okay. So therefore, we need namespaces. I guess this is repetition. You already know how to do that. Namespaces, yeah. So we have already seen how that works. And we need virtual Ethernet devices. You also already know how that works. So I don't want to repeat it now. I'll repeat it very quickly when we go through the tutorial. So virtual Ethernet devices are created like this. We already know that. What we don't know so far is how to create a virtual bridge. I mean, a hardware bridge. I go to a store and buy it. Yeah? Then I have a little box and I put it on my table and I plug in cables. Yeah, no problem. Which command do you think will be used to create a bridge in Linux? Because I so often now said the one command that you always use to configure a network device is always the command blah blah blah. IP, yes, it's always IP. So you see, the tutorial works perfectly, yeah? And it's, of course, IP link because we create a link layer device. Yeah? A bridge belongs on the data link layer. Ethernet belongs there. Actually, Ethernet is physical and data link layer. Yeah? So this is what we do. We use IP link, and we would like to have a virtual bridge. And a virtual bridge gets a certain name. We call it here vBridge. You can also call it Hans or Franz or whatever you like. And then this is the virtual bridge that you have. You have to bring it up. Okay, great. And then you want to attach maybe some network devices to it. For instance, you want to assign here your physical device to the bridge, or you want to assign these virtual devices to the bridge. How do you do that? You say that, and here I have to say Linux is not so inclusive as the IEEE standard that Mahin mentioned previously. Here it's still the master. Yeah? So IP link said virtual Ethernet device so-and-so goes to the virtual bridge. That means the virtual bridge becomes the master of that device. And now suddenly it's attached to the bridge. It's like plugging in the cable. You plugged in now the virtual cable into the virtual bridge. Okay, and if you combine that TA Prio plus the virtual bridge, then you should have a virtual TSN bridge. Yeah? I don't want to say this is the dream of everybody, but first of all, if you are a PhD student, then it's a very cheap way to build a TSN network. You don't need to buy any hardware. Okay, don't tell that your supervisor. Yeah, of course you tell your supervisor you need to buy the newest hardware from some favorite vendor because they sell great TSN switches. Clear, yeah, of course. But if you want to play around with it a little bit, then maybe the software TSN bridges are very nice, yeah, or would be very nice. But beyond that, I mean, in reality, they are required if you want to extend your TSN network into the virtual world, onto the virtual machine, or up to the virtual machine. So it's not only a toy, it's maybe required, yeah, in practice also. I mean, there's a reason why companies contributed that to the mainstream Linux kernel. Okay, so you create a virtual bridge, you create virtual Ethernet devices, you assign the VLANs and the PCP mapping, and then you have with TA Prio on the right interfaces, you have a TSN bridge. Sounds so easy, and you will do it. It's so easy. No, don't worry, I will not sit down again and show now in the virtual machine how that works, but I want to say you have the virtual machine. I will show you now all the steps with the slides because they're all on the slides. Really step by step, one by one, up to the point where everything would work, but you have to try it yourself because this time I want to be on time. So in last time it figured out either I'm a slow writer or I have too many things on my slides. I guess both. Okay, that would be the last tutorial for today. Build a software TSN bridge with Linux. And basically you have all the ingredients now. You should be able to solve that task yourself. But of course we try together. Yeah? So what we want to build is this here. We have two namespaces, talker and listener again. We have the virtual bridge. We have virtual Ethernet devices connecting the namespaces to the virtual bridge, because that's the best thing we can do on the virtual machine that I provided to you. So no connection to the outside world. You could do that, but if you mess it up, you have no internet connection anymore. Okay, for a virtual machine, not so bad, I guess, but maybe you don't want to have that. We need something with VLANs. So the VLANs would be actually attached to the namespaces, talk and listener here, because we need to map the SKB values to the PCP values, so we need a VLANs. And we also need TA prio, so the flow of messages will be from talker namespace to listener namespace. So therefore, TA prio is at the egress interface. So this is where the scheduling will happen with the timetables and the gates. But in order for that to work, we need on the other side a filter, a QDisk filter, which makes the mapping from the PCP values of incoming packets into the bridge to the SKB values. Yeah? Because this guy here, this understands no PCP values. This only understands SKB priorities. But what flows into the bridge is something with a VLAN and PCP value, and therefore we need to map that again to an SKB. Yeah. And this is what most people forget or don't find. They find this here. This is quite easy to find, but they forget this here, and then they think you cannot build a software TSN bridge with Linux maybe, but you can. It's just a little bit configuration. Yeah. Okay, so going step by step. Creating namespaces. I think this is boring now for you. You're already pros in that. So sudo IPnet namespace at talker creates the talker namespace. Sudo IPnet namespace at listener, the listener namespace. And if you type in these two commands, you will see there is one namespace for listener and one for talker. You have already done that today, and you have already seen that. That's not big black magic anymore. Then we create a virtual bridge. We've already also seen these commands, but just to repeat that, it's the IP command, it's link, because we're on the link layer. You add a virtual bridge with the name virtual bridge here. It's of type bridge, because it's a bridge, that's what it is. And don't forget to bring it up, otherwise it just don't work. Yeah? It's a little bit cumbersome, this bringing up of all these devices, but we just do it and then the bridge is running. It's like hitting the on button. Yeah? Now the bridge is already there, but nothing it's attached to the bridge yet. So therefore we create first of all virtual Ethernet devices, and you remember they come in pairs. It's like one network device, another network device, and a cable in between, a virtual cable. Yeah. So we create two of them, but for the second one, so the one here on this side, we have to remember that TA prio needs 8 transmit queues, because we need that for having the gates before the queues, and if there's not 8 of them here, it will not work. So TA prio would say, I don't work on that device. So therefore we say for the second device, and that's the new thing compared to the other task that we had, we want to create this number of queues for this device. In that case, 8. Huh? You can never go wrong with 8 transmit queues in TSN. Okay, great. Then these links should go to the bridge, of course. Now, first of all, we create VLANs. Okay, so what we do now is, looking at this here, we now create this part here. So far, we have only these two things. And now we want to, oh, there's my mouse pointer, it's not visible here. Great. So I could switch it on now here. There's no pointer. So now it's visible. So far we have only this pair, but now we want to create this here on top, which is responsible for the VLAN ID. And also not a big magic now anymore. So we say, given the one virtual device, create a new one called 8.100, and this belongs to VLAN 100. So this is coming on top of the one device, and for the other one too. So, and this is always the side facing to the namespace. And then we connect our namespace devices, or VLAN devices to the namespace with the IP link set command, and the other side to the master bridge, or to the bridge, to the virtual bridge. And now suddenly we have this picture here. This picture, but so far without TA prior and without this SKB filter. Yeah? But we're almost done. Yeah. A lot of time left. Okay, we can already test it by assigning, first of all, going into the namespace, running a shell there. If we are inside a namespace, the talk and listener namespace, we can assign IP addresses to the VLAN devices that we have assigned to the namespace. We already also did that today. Here, the one device gets the IP address 10.0.1.1 and the other one 1.2. And now it should already work as a bridge, but without TSN so far. But you can already communicate now via a bridge with the other namespace. Previously, we had a directly attached cable, you could say, with one namespace and the other. Now we have a bridge in between and it works. Well, but it's not TSN yet. So how do we make it TSN? Huh? How do we make it a TSN bridge? So first of all, we need to define a mapping from SKBs to PCPs. Huh? So we already know this is simply done by this set command here, and at the end there's the real mapping. So we map the SKB value 0 to 0, PCP 0, and 1 to 1. That's here. There, it doesn't hurt to also do that for the other side, although our traffic only is flowing one way in our example, but in reality you would define it for all the talkers. Okay, that's good. Now we need our TA prior Q disk. We need to assign it at the right place. So what's the right place? The right place is the interface facing to the listener, because the shaping happens here. When the traffic goes out here, it should be following the timetable entries with open and close gates. So traffic flows from the left to the right, and the direction to the listener is via this Ethernet interface here. So here the shaping happens. So to this device, we assigned here a prior. Here. We already know the syntax. We know it's cumbersome. We know we have to look into the man page to figure out what it was. Yeah. And believe me, after 1 hour, I've also forgotten about it again. But this is maybe my problem. So the interesting thing here is in our example, we have one gate for one priority open for, here it's 500 milliseconds, and the other one for 100 milliseconds. So it's asymmetric, you could say. The one traffic class gets much more time than the other traffic class, and it's quite coarse-grained. It's, let's say, not nanoseconds open and then closed again. So we should see an effect. If we send traffic later on, we should see a effect there. And that's the whole idea here. We say the traffic class 1, or actually starts at 0, so traffic class 0 has this opening time, and traffic class 1 has this opening time. Okay. If you have configured that, it would already do some shaping, but possibly not the thing you want, because what we want to do is we want to have an SKB value mapped here. You see that here in the mapping. Where is the mapping? No, here. It's a little bit shorter than usual. So the SKB value 0 is mapped to PCP1 and the other way around. Yeah, or traffic class 1 and the other way around. So it's a cross, let's say. Yeah. So if you would run it like this, then suddenly you would see it would do the shaping, but it's not getting the right opening time. It's getting the other opening time. So we have to define now somehow this mapping of PCP values from SKB values at the ingress. So what's still missing, if you look at the picture, is this here, this SKB filter. There is messages going in here, but they all get the SKB entry 0, the default value. And here prior is always using 0 for the scheduling. What we want to do is that priorities SKB, PCP 0 should be 1 here at the SKB and the other way around. So we need to define this filter here. And if you promise me not to share this slide, then I can show it to you. If you show it to the whole world, then the whole world has one question less that they could ask us. But this question is coming up again and again and again, and I also have to credit to one more colleague in the Data6C project. There's different ways of doing that, but this is the most intuitive way. So actually, this is the way that is more readable, let's say. SKB edit, we map the VLAN priority 1 or PCP 1 to priority 1 in the SKB. And so this is how you can do that. By the way, this priority here, don't mess that up with any other priority of TSN. This is the priority of the filter. You could have many filters on the ingress device and can define also their priorities. So priority term is heavily overloaded. This is what we do. And now we would test it if I had now followed all the steps in the virtual machine. Maybe you did. Let's see who gets a distinguished training day award from the listeners. Then we would run it now. I have, what do I have here? Yeah, maybe this is also interesting as a side note for all the networking guys. Computer scientists are lazy. Yeah, okay. Typically, you reuse software. I know, typically it's the other way around. You say the software of another programmer is bad, and I'm the only good programmer in the world, therefore you rewrite all the software, of course. That's how it works in reality. But how it should work is you should reuse the things that are already existing because they are battle-proof and you should use them. So what is NC? NC is Netcat. And this is like the Swiss Army knife of networking. It can send UDP traffic, it can send TCP traffic, it can receive UDP traffic, it can receive TCP traffic. What more do you need? If I need a listener, then I just use this here. I don't write a single line of code. I just use what's existing, and that comes with every Linux distribution. So we say a UDP listener listening on port 6666, and else means listening, means it's a server. So this is a UDP receiver. It receives something, and then it discards it by sending it to device null. Device null, you know, is basically it transforms bits and bytes into heat. So it throws it away. Device 0 provides you with many zeros as input. Device null means throw it away. So we don't need anything here in terms of data. We throw it away. And then we want to see what happens at the receiver side. And for this, we use another tool called TCP dump. If I want to monitor what's going on a device, TCP dump is your friend. And TCP dump is not only for TCP, it's able to record all the frames going into a network device. It's running in promiscuous mode. Only a root can do that, of course. And then you can record everything going in over a network interface. It writes it to a so-called PCAP file. And this you can later on visualize with many tools. So here we listen on this interface here. We write it, the trace, to a PCAP file with nanosecond timestamp resolution. So every frame that is received gets a timestamp. So we can see later on what the pattern is of the packets that we have received. And then we start a sender, which is now my own cyclic UDP talker here. And this one is sending traffic and also timestamping it, I think. But we don't need the timestamps here. We just look at what happens at the receiver side. And then theoretically, I would have shown you now with some Jupyter Notebook and some more tooling here what the trace would look like. So I wanted to show you this here. I know now the people online are a little bit on the bad side. So I wanted to show you a timeline, basically, let's say from 2 seconds to 3 seconds. And I wanted to show you lines here when a packet is received. And then we should have seen a certain pattern. So what kind of pattern would you expect? So every line is a received packet that is received by the listener. And we are shaping the traffic we're only sending traffic with one priority. I'm not even sure anymore, was it 0 or 1 or whatever, but only one priority, and the gates are open 500 milliseconds for the one priority, 100 for the other. After 600 microseconds, the whole thing repeats. Yeah. So what kind of pattern would you have expected here? Yes, many lines and then a blank. Yeah. So like this, and then nothing, and then again a lot of packets received, nothing, again a lot of packets received, and so on. Because here the gate is closed. That's where it's closed, yeah. And in the other intervals it's open, yeah. And the intervals should match what we have configured, yeah. And the cyclic sender sends relatively fast, yeah. And it would like to send also here, and it also sends during that interval, but it gets caught in the buffer. And only when it opens, then the buffered packets are transferred further on. And as said, you can try it out. It will work. You will see the pattern, but you have to do it yourself now as a homework, because I think you appreciate that I don't sit down now and put that everything in a virtual machine. But you have the virtual machine. You can try it out yourself and then figure out whether I'm lying or not. If it doesn't work for you, send me an email and then we can discuss it. Then you get some, not a full grades, of course, yeah, for this task. Okay, so that actually is the end. It's the end of the training day and of all our tutorials. I know it's like a sudden death now. It's a little bit suddenly that we are at